Hi everyone, I'm Arnaud De Coster, a researcher at the VUB in Brussels, and I will present my research about the measurement of the aero-elastic movement of fabric structures through an experimental approach. Before starting, I would like to thank the organizing team of the conference to make everything possible virtually. So big thank you for this. Fabric structures form a unique part in technology. They allow designers, architects, and engineers to experiment with fabric shapes using load pods to create exciting structures which are visually attractive, but also competitive on a structural, environmental, and economical level. Advancements in the technology of fabric structures are continuously taking place as researchers are working towards one unified code applicable as a general guideline. Wind analysis of fabric structures is currently based on rough approximations, referring to flat, mono, duopitch, or spherical shapes of the Eurocodes. Large displacements caused by wind require a good understanding of the interaction between structure and wind pressure. The analysis about this interaction can be decomposed in a numerical part and an experimental part. In this research, the focus will be set on the experimental part. Nowadays, three main approaches for the dynamic equilibrium study of fabric structures are applied. Going from rigid to aero-elastic models, we have direct pressure measurements during wind tunnel testing, direct measurements of the overall reaction forces by load cells, and as a third, a combination of optical measurements during wind tunnel testing and numerical fluid analysis. For deformations of flexible fabric structures, however, it is more the domain of the digital image correlation that starts to gain interest for further investigations. Digital image correlation is a full-field image analysis method applied on gray value digital images to determine the contour and displacements of an object under load in 3 dimensions. A stereoscopic camera setup is used around the model to achieve a 3-dimensional interpretation. This research enabled to obtain a method in which precise membrane movements are being detected. It was important to gain knowledge in the optical background of the system by understanding the link between its intrinsic and extrinsic parameters. This ensured a base to achieve proper measurement conditions and hence reliable results. Wind is a highly dynamic load case in its nature, being difficult to characterize or predict. The global goal is to understand how the wind will affect these lightweight fabric structures to ensure an improved structural safety over the lifespan of the design. Presently, little experimental work has been done on the response of fabric structures under turbulent wind loads and how structural parameters affect this behavior. Tested under stiffness, flexibility, and paint absorbance, poplin fabric has been chosen for the flat membrane and lycra fabric for the higher flexibility for the hyper. The edges of both membrane configurations have been pulled over polyamide cables, being tensioned from pole to pole. In a first stage, tests have been performed on both static models, first with a laser distance meter, and afterwards confirmed within the DIC software by tracking down the same locations of the marker points. When the height differences were correctly measured by both systems, it became time to measure it in the wind tunnel test section. Here, both model visualizations within the DIC software with accurate height variations. So, 20 tests have been performed on different membrane configurations, subjected to increasing wind loads. Pictures were acquired at a rate of 1 per 300 milliseconds in a time frame of 1 minute. Per model configuration, 4 wind tunnel tests have been performed with increasing wind speeds of 3, 6, 9, and 12 meters per second. Per test in a wind tunnel, a new calibration of the system was done to ensure good measurements. Working with a flexible membrane, it was difficult to predict the exact behavior of the wind around the model. Two possible phenomena were possible in the case suction appeared. First, a positive lift force due to the faster flowing winds above the surface in comparison to the area underneath. Second, the appearance of a separation point of the flow causing a lower pressure area, which also influences the pressure drag. By understanding the workability of the DIC system, after going through different stages of study, positive outcomes were achieved during the measurements in the wind tunnel. Proportional behavior could be observed, and movement along the increasing wind speeds could be related to a theoretical as well as physical reality. Small deflections as well as dominant deflections were well visualized by the DIC software, with clear zones of influence being divided along the surface. Fluctuations of different orders could be well perceived in between the different pictures, going from 1 until 10 millimeters. This proved the precision of the system as well as the setting which was built for it. So as a conclusion, a DIC measuring methodology has been reached as a framework for future experiments on the wind behavior of membrane structures concerning the displacements on flexible models. Future perspectives involves the investigation of a set of structural parameters on the behavior and associated with CFD results. This will help to better understand the dynamic structural behavior of fabric structures and increase their structural safety by applying the right designing manners. By comparing different membranes based on stiffness, weave, and material differences, experimentally and numerically, a larger designing scope for membranes could be reached. Thank you for listening.